welcome you on the third day of ICC SA 2025. On our third day of ICC SA 2025, we are pleased and glad to have Professor Kaan Mohammed from Sungang Unvan University, Department of Applied Artificial Intelligence, South Korea. As our keynote speaker, before he delivers his keynote speech, I would like to provide you with a brief biography of Professor Mohammed. Professor Kaan Mohammed, as a senior member, IEEE, received his PhD degree in digital contents from Sojang University, Republic of Korea. In 2019, he is an assistant professor with Department of Software, Sejong University from 2019 to 2020. He is currently the director of the Visual Analytics for Knowledge Laboratory and associated professor with Department of Applied Artificial Intelligence, School of Convergence, College of Computing and Informatics, Sungwon University. The research interest of Professor Mohammed Kaan, intelligent video, surveillance, medical image analysis, information security, and multimedia data analysis. He has registered 10 patents and has contributed over 200 papers in peer-reviewed journals and conference proceedings in his areas of research. He is an associated editor and editorial board member, more than 14 journals. He is also among highly cited researchers in 2021 and 2022, according to Web of Science. Yes, Professor Kaan Mohammed, we can kindly invite you to stage so that you can deliver your keynote speech, which is entitled Intelligent Image Enhancement for Real-World Application in Adverse Atmospheric Conditions. Over to you, please.
Good morning, everyone. As Dr. Yil introduced, I'm Khan Muhammad from South Korea. First of all, thanks Dr. Yils, the President Osvaldo, and other committee members for inviting me as a keynote speaker to this conference. Yes, should I? The slides are not moving. Excuse me. Can you check?
It's not working yet.
Should I check from here?
Okay, you can press here, please. Okay,
Then I will stay here.
Yes, please.
So in today's talk, I will be talking about these topics. First, I will introduce myself a little more. There are some contents that I have included, especially for graduate students and for young researchers, how to motivate them for certain achievements that I have tried with my team. And a few topics on which I'm personally working or with the other researchers around the world. And some of my team members I want to introduce, especially those who have secured good position under our supervision. Then I will introduce the topic with some challenges. And within this research area, we have two main contributions. These two contributions are selected carefully from the BK conferences. We have a list of top tier conferences that's also followed in different universities around the world. Although it is a bit debatable whether to select journals or conferences, but since these are our recent contributions, I try to include them as a keynote speaker in the talk. And finally, I will conclude this presentation with some future direction. And of course, I would like to hear your feedback too, how we can improve this research area further. So this is a little introduction about me. I personally recently worked in dehazing, image enhancement with some teams on personal re-identification. And another interesting area that I'm mainly focusing is about child aggressive behavior recognition or hazardous activity recognition. I believe for many of you have children here, so this is very interesting area, and we have developed some good research and data set how we can save our children. Um, as also Professor Ariel talked about disaster management yesterday, so I have also worked in this area, and we have some discussion yesterday about fire detection, fire segmentation, and fire scene analysis or context analysis. Disaster management is a broad area, and our focus was on fire scene analysis, uh, including smoke detection or smoke segmentation. Uh, if you talk about our works, we have presented our works in conferences in different countries. You can see a few selective conferences here in different countries. So far, I have supervised or co-supervised more than 20 PhD or master students, and all of them are at good positions in different countries. Some selected students you will see in a while. This is somehow an overview of our research areas. Mainly, I work with 20. I work with more than 100 researchers, which are from more than 20 countries, and these are some research topics that are related to me and my team. It includes disaster management, video surveillance, coastal surveillance, which where we focus on rip current analysis, aerial detection and mitigation, which is also a recent topic, and mainly it is motivated by the recent accident, the airplane that crashed in Jeju, in South Korea, in which many people died, and also in India recently there was a crash. So we are trying to make some data set and some system how we can avoid the aerial hazard, especially about the drone and about the bird strikes. And although this is in the preliminary stages, we are going to release the data sets and the studies soon. Beside this, we have some works in autonomous vehicle, action and activity recognition, wireless detection and analysis, video summarization, on which I have worked before. So the reason to explain all these is to let the students and the audience know what are our topics and what are the different areas where we can possibly collaborate. As I mentioned, we have collaborations around many countries, including US, Europe, Spain, Italy, and Turkey, around the Middle East. Some of the key members are mentioned here, like Intelligent Media Lab from South Korea, and that is my the university from which I graduated, Sejong University. Digital Image Processing Lab, Pakistan, and then Well Laboratory, that is a visual AI laboratory from UK, uh, Color and Visual Computing Lab from NTNU Norway, Data 61 from Australia, and Technalia from Spain. And these are some key students that I have supervised, starting from Dr. Amin, who work on action and activity recognition, and he is now a senior AI and machine learning engineer and Boeing R&D in USA. Dr. Ijaz, he worked on movie summarization, and now he's a postdoctoral researcher at Michigan University, USA. Tanvir, he worked on multi-view video summarization, which is very common in surveillance, and he is now a lecturer or assistant professor at Edge Hill University. Salwan have worked with us during the master degree, and he joined Oxford Brookes University for a PhD, followed by his postdoctoral position now there. And Dr. Fatou has mainly worked on violence detection and recognition, and now he is in UCL University, UK. Yeah. Similarly, Dr. Nasser has completed master during our supervision, and then his PhD in Sungkyunkwan University. The word Sungkyunkwan is a little difficult, so you can say SKKU. It's a simplified form. Now he is also postdoctoral researcher at University of Michigan. And these are some of our active members which are working with us. Is the below list my own students under my direct supervision. I prefer to have international students and somehow remote supervision, but as a regulation, we have to also supervise students locally. The works that I'm going to present are mainly from Mr. Tanvirul Islam, who is originally from Bangladesh, and the studies are mainly conducted by him under my supervision. Now he is a PhD student. Now, coming back to the topic, there is intelligent image enhancement, mainly for adverse weather conditions. We all know that in the developed world, we have cameras installed everywhere, right? In Istanbul, you can see in every street we have cameras, and they are used for many applications, including smart surveillance or other vision-based system. But when we have adverse weather condition, like haze, fog, smoke, or snow, their performance is affected. So here I have added some statistics like weather impact on road safety. If you look at the WHO report, worldwide approximately 1.19 million people die every year because of road traffic crashes. And this is a huge number if you think about it. In the US alone, more than 38,000 vehicle crashes occur in fog, in which 21% are related to weather. In Korea, although I couldn't find the latest statistics, in one report we found that the fatality rate is 6.9% on foggy days. But in the normal or clear environment, it's just 2.5%. For Istanbul and for Turkey, I checked many papers, but I couldn't find any statistics. Mainly, they were not public. And I somehow found that in Istanbul, on average, we have 60 days, which the environment is foggy and it affecting the vision-based system. So these are some statistics which highlights how important this topic is, image enhancement. If we talk about the challenges in vision, poor visibility from haze or low light makes it difficult for system to detect objects and navigate safely. And if we talk about self-driving cars or surveillance systems, they need clear vision to make safe and accurate decisions. Since the work is mainly related to a master thesis, there is a problem statement mainly for a single image dehazing. Most existing methods assume a single haze uh, uh, or work on synthetic data, and we have not large data sets. Lack of large data sets or diverse data sets. This point was also highlighted yesterday by Professor Ayar, that we need more label data set in order to train good models for deep learning research. So as a general audience, if we talk about image enhancement, you can see the first figure. We have an input image, a hazy image, where the objects or the environment is not very clear. And if we apply the enhancement algorithm, as a result, as an output, you can see the image is very clear. This is the basic idea. But how it is different from intelligent image enhancement? When we talk about intelligent image enhancement, it should consider all the different aspects that you can see in the second figure. That is haze and fog. The algorithm or the system should be able to take care of haze and fog that present in the images captured by surveillance camera, because the haze and fog can reduce image contrast and color fidelity, which cause poor object detection and scene understanding. Another aspect that the intelligent image enhancement has to take care of is low light. Low light. Low light leads to underexposed images with missing details. It degrades the feature extraction for different recognition tasks. Similarly, the rain and snow, which is also common in many countries, uh, the intelligent image enhancement system has to take care of this matter, because it obstructs camera lenses and introduce artifacts which are confusing vision models and tracking systems. Besides these three main categories, it has to also deal with the latency and sensor noise. There is some further motivation why this research is important to and applicable to our lives. It has application in autonomous vehicles. because they are mainly also working on vision based data in images or videos. It's important for surveillance. It's important for aerial monitoring, including the airlines, as I mentioned, for traffic monitoring and smart cities, for precision agriculture, where we have to take care of different applications related to agriculture and aviation. On the left side, you can see some major impacts due to adverse weather conditions. If we consider autonomous vehicles, due to haze, fog, or low light, it reduces the object detection and tracking accuracy, and you can see up to 30% drop in performance. In surveillance, the error rate increased by around 40% under haze or low light. In aerial monitoring, 80% of the drone failures linked to visibility issues. And last but not the least, agriculture, over 40% accuracy loss in automated crop analysis in hazy conditions. So these are some further motivations which help us work more in this area. Now, talking about our main contribution, we selected two papers. The first one is Haze Space 2 million. This is a data set, and there is a proposed work. We call it haze aware single image dehazing. And the second one is LoLI-Street, followed by a new method, that is tri-fuse. We will see them in a while. As a result of the master thesis of this student, he has these contribution. There are some other co-works, but mainly we were successful to file patents which are already registered. And the two publication, one is from AC Multimedia. In Korean terminology, we call it BK MP Factor 4, and I think in the Australian system, it's called A-STARS conference. And similarly, the second one, which is also computer vision conference, Asian Conference on Computer Vision, is BK MP Factor 1 or B conference. The first contribution, you can see we have different image types. Unlike other data set which has only one type of haze or abnormality, we have tried to include multiple haze types. How our data set is different from them, I will explain in a while in the table. When making the data set, we try to apply some constraints to ensure the data quality. The first one is we selected a resolution threshold, and we excluded all those images where the haze was ambiguous and not very clear. And in some images, if the content are unrelated, we just excluded them. Here is an overview of the data set. If you look at table 1, haze space 2 million, we have outdoor environment. We have data from outdoor. We have data from street, farmland, and satellite. But in existing data set, they usually follow one or two categories. If you talk about the type of haze or things that are included, we have included fog, environmental haze, and cloud. And talking about table 2, there are existing data set from which we have picked some data, and then we have applied different synthetic effects to introduce the images or make the images. Table 3 is mainly about the number of GT images, the number of hazy images, how all these are formed, including the real haze test set that you can see at the end. Overall is 2.2 million images, which is the biggest data set so far in the literature. In table 4, you can see the comparative analysis. The existing data sets are there, what type of data they have covered, outdoor or street mainly, or some have covered satellite. In our case, we have 4 types of data. Similarly, haze types, you can see the existing have 1 or 2 types of haze only, but we have covered 3 types. And the lowest haze level, highest haze level in terms of PSNR and ISSIM, the values are calculated. Now, besides the data set, as I mentioned, we have this idea of haze-aware dehazing. The existing methods, we have an input image, and they just apply dehazer. regardless of the fact what type of haze is there in the image. What we did, we tried to first analyze the image to find what type of haze is there, and then we selected a specialized dehazer to dehaze or clear the image. And it's a bit journal framework, but you can see in block A we have a training block that is a haze type classifier, and then in block B we have a classifying block. C is about how to select a dehazer, and finally the dehazing block, which perform the actual dehazing. These are some dehazing results. You can see we have a list of deep learning models and their accuracies. Table 6, you can see we have mainly LDNet. This is also one of our contribution, which is published in IEEE transactions and image processing. And GDNet is the generalized dehazer, and SDNet is specialized dehazer, the method that we are claiming to in this work. So if you look at the table 6, we have different tests from home, environmental, haze, from cloud, then the existing LDNet, the GDNet, and the SDNets. You can clearly see in case of single haze aware dehazing, the performance is better, and it's quite a big improvement in the performance. These are some results about haze type classification. You can see we have the green color is the actual classes, and the predicted class and the probability is given. This is mainly from ResNet because based on the previous table, table 5, we selected ResNet as the best model. It has the better performance compared to others, so we just tested it for haze type classification as an example. Here are some more results, mainly state-of-the-art dehazers, and when they are tested using the pre-trained weights, you can see the results. And when they are trained using our strategy, you can see there is a boost in performance. Table 8, you can see we selected 3 state-of-the-art or best performance from table 7, and then we applied them to different foggy data sets that are from other researchers. And you can see in FRIDA or cityscapes and fog type of our data sets, the performance you can see is less compared to others. Why? Because our data set is more challenging. This means compared to FRIDA and cityscapes, our data set is more challenging, and researchers have to try to develop more intelligent and good works in order to beat the performance and try to improve the accuracy and other metrics. There are some visual results too. You can see on the first column we have the hazy image, and on the rightmost column we have the GT or the ground truth image, and the result for LDNet, GDNet, and SDNet you can see. And the second column from the last, you can see the images are very clear and very near to the ground truth images. Also the PSNR values are higher. Now, coming to the second contribution, that is about LoLI-Street. Again, this is a data set, a new data set followed by our work, that is TriFuse. This work has 33,000 peer low light images. We have low light images, and they have 3 levels. Also, we have a real life low light test set. This is also very important. Otherwise, if all the data is synthetic, it's not very realistic. So we have to include images from the real environments. If we compare this to the existing data sets, you can see table 9, where we have data sets from different top venues, including PMVC, IEEE TIP, CVPR, ICCV. And compared to them, the number of images in our data set are more. There are some sample images, as you can see in figure 7, and then some quantitative analysis of our data sets in table 10 for training, for validation, and for the real test set. There is one important observation that you can see, and I think it will be very helpful to the young researchers. We have used these arrows. some of the metrics are very common and everyone can understand that the PSNR, the maximum, is considered the best. And similarly, SSIM, the same. MSE, the minimum, is the better. But some metrics are not very well known to all the audience or the students, especially when we submit papers to conferences or to journals. So we have to make it very clear what is meant by each metric, and we write or include these arrows, so it's very helpful to the reviewers and the audience to understand the impact. Now coming to the TriFuse, we name it TriFuse because it has three main modules. The first one is a conditional noise module, which learn the noise pattern based on the input features to guide the denoising process, and it is marked in the yellow in the figure 8. The second part is diffusion denoising, which applies a reverse diffusion process to recover the clean features from noisy inputs gradually, and you can see it in the light green color. Last one, each sharpening module, which enhances the structural details and sharpens edges using residual blocks and attention. Some tools, Python, NumPy, and others are used when making this data set and using this algorithm. Some further details about the diffusion denoising, low light image enhancement. Mainly, the TriFuse breaks the input image into low light image and the low light image into low frequency and high frequency components, as you can see in the equation. Why we do this? This helps in separately handling brightness, that is a low frequency, and fine details, that is a high frequency. And then we have forward and reverse diffusion. Forward diffusion gradually adds noise to the image over multiple steps, and this process corrupts the clean image step by step, so that the model learns how to recover it later. And the reverse diffusion, it starts from the pure noise and it progressively restores the clean image. Here are some more details about conditional noise module and its sharpening module. You can see more details in the paper too, so I will skip this slide. Coming to the quantitative results, we have table 11. We are based on the pre-trained weights of each model. We have different results in terms of existing methods and our method. Again, all the metrics are given along with the different upward and downward direction. Table 12, we have SOTA models compared to our TriFuse when it is trained on our data set. And you can see the different results. The bold result shows the best results, and the underline means runner-up results. Table 13, we have comparison of main SOTA models and real low light test set. You can see the different results. Table 14, we applied it to the real world application object detection. If we apply our method to the low light images, how it can improve the object detection. So for that, we have this experiment, and you can see the different metrics. Our method, that is the last column of the table TriFuse, you can see has the best performance. This is further about comparative analysis in table 15. You can see different SOTA models on mainstream low light image enhancement data set. These are different existing data sets and existing methods, and you can see the results. Besides our own data set, the results are better in terms of other data sets when we have used. These are some further analysis, visual quality and efficiency comparison. Mainly, we also add when we talk about the top tier conferences. At the start, you may see a similar figure, which is very important and catchy to attract the attention. On the first figure, figure 9, we have Bristol metric and the inference time and the different methods. So you can see our method is a better balance between the efficiency and the quantitative comparison. And figure 10, we have a real low light image, a sample image, and its part has been dehazed and clean using our method and different SOTA models, and you can clearly see our result resembles the ground truth, are more realistic. This is some further visual comparison from different SOTA models. Again, some more results. This one is a real world application, as I mentioned before too. But here we have added a visual example. You can see the first row, left image, we have test image, and then we have different methods. The low light image is enhanced using existing methods and our method, and then we try to detect how many objects are there. This is very important for autonomous driving or other vision related applications. So in our case, the tri-fuse, you can see it has selected the cars, buses, the TL and IT, or everything is selected. In terms of IT, there is inference time. Our method is also a better one. Here are some further results. Table 16, detected objects across different subsets of our LoLI-Street using YOLO V10, and the class ID and other information are given. In this case, we have selected some randomly images from different mainstream datasets, and we try to apply our method. And even in this case, you can see the performance or the quality is quite better. These are, as I mentioned at the start, in case of LoLI-Street, the images are from street images, right? But these images are from non-urban streets. And if we apply our method, still the performance is better. In intelligent image enhancement, dehazing and low light image enhancement are not the only two problems, and there are other sub-related tasks that can help us intelligent image enhancement. For example, image deraining. In every country there is raining, and as a result, the vision-based systems have limited performance in rainy environment, and this technology can help us. Image deraining. Similarly, image desnowing. In many countries, we have snowy environments too, including South Korea, and we can apply image desnowing to improve the performance of different vision-based application. Last, which is also very interesting and somehow very challenging too, multi-weather image restoration. This is mainly important for real-world application where the weather is unpredictable. And its applications include autonomous vehicles, remote sensing, outdoor robotics that are operating in unpredictable conditions. What can be the challenge? Different weather types introduce diverse degradation patterns that require models to handle varied textures, contrast, and occlusions. The recent trend is joint weather restoration model like unified transformer frameworks. We have a study about this too, but it's in a preliminary stages. Unlike existing methods, which just focus on a single type of haze or vulnerability, what if we have an intelligent algorithm which can work for all? Like we have algorithm which can dehaze an image, which can derain an image, which can desnow an image. All of them, it can be performed. Or there is another aspect of this terminology, multi-weather. We can have a situation where multiple weather conditions happen at the same time. So how the method should be intelligent enough to take care of such situations. So we have these methods, and in the upcoming years, we will release everything. It's also important to mention that the two datasets, LoLI-Street and Haze Space 2 million, they are already available publicly on the Hugging Face website. So you can see from there and you can download and use it. I would like to conclude. We develop robust pipelines for image enhancement for adverse weather conditions. And mainly we have two contributions, the two datasets that are real world datasets and have application in many areas. And we try to propose adaptive solution to improve the image quality and the downstream vision task. One example was about the object detection. Of course, there are limitations in our works. The first work, which was a haze aware dehazing, It's mainly dependent on the haze type. If if the haze classification algorithm fails, the next result, that is dehazing, will be somehow wrong or can be poor. And wrong classification, yeah, this already mentioned. Training data are synthetic and may not cover the real world complexity. Although in the data set we have real test set, uh, majority of the data was synthetic. So it's very challenging to include real world data. Future scopes can be, we can make a unified method which can dehaze multiple haze types. We can develop models which are computationally less expensive. And finally, which is challenging and very impressive, intelligent image enhancement method for multi weather artifacts like snow, rain, haze, fog, and so on. These are some references. Thank you very much for your attention. Tashakkur diram. If you have any question, feel free to ask, or if you have any suggestion how we can improve this one further, feel free to comment. Time. Any question? Any suggestion?
I got one question.
Yes, please.
Congratulations for the presentations.
Thank you.
Fantastic presentation.
Thank you.
My question, I wonder to know, did you get the synthetic data to train the algorithm?
Can you open the PPT? Okay, I mean, we have used different tools like Photoshops, and the students, the students these days are really smart. They have different ways how to add synthetic effects. So although this is more than 2 million images, we have many computers to make some editing and make all the images. And so mainly we use Photoshop and some other tools to add the synthetic effects.
Do you think that virtual reality can help you defining some environments that can increase the synthetic data generation?
Pardon, please?
Instead of Photoshop, do you think that virtual reality tools can help reconstructing some specific environments for enriching the synthetic data generation?
Yes, if you have seen the images, we compared with other data sets. So and we proved that if even we have used synthetic data, our data set was more challenging to others. This means it's reflecting the actual environment. And also, you saw in the presentation that we have real test set on which we compared our method with others, and our results were better. So we do believe that it reflects the real environment. Any question? Yes, please.
Yeah, thank you for the talk. Very interesting. I work mainly in the medicine area. One of the problems in medical imaging, like MRI, for example, um, that you have some object in your body that actually interfere the magnetic, the MRI, and therefore certain areas may be blurred because of the infraction. Like for example, your pacemaker, any other things in your body. Have you considered, because you are working on like images that are blurry because of certain condition? Have you considered maybe in the medical area where the blurry is difficult, it's different from the normal phenomena because of the foggy or whatever, but because of interference with the objects?
I think it's a good direction. So far, as I mentioned, these are our first contributions in this area, in single image dehazing and image enhancement. We recently started work, but we have not explored the possibility of low light image enhancement or single artifact in medical domain.
that we can consider. As Yates mentioned, we have worked in medical image analysis, but that is mainly brain tumor classification or grading or some medical video summarization or something like this. Yeah.
Yeah, like brain tumor detection and so on in there.
So
Probably easier.
we have not explored this topic in terms of medical imaging yet, but it's a good direction we can work on it. Yeah. Any further questions? Yes, please.
Thank you for this beautiful presentation. I was wondering how you test the data, because does it only work for long shots or street view, or does it work for short distance photos? Did you test it? Because it might be used for entertaining purposes, maybe for movies or filters.
In the data set, we have a variety of data. Mainly, the data is taken from existing data set that you saw. So all the details of those data is already public. So I think we can see from there what aspects are considered in order to make data sets. I just cover how we pick those data and how we apply the synthetic effects or different haze levels. I think I missed. We have 10 levels of haze for each input image, and accordingly the data set was generated. And in case of LoLI-Street, we just consider the street images because our purpose was mainly the focus was mainly on autonomous driving, how we can help the autonomous driving, and because we have some follow-up patents about the autonomous driving technology. Any further questions? Yes.
Thank you, Professor Khan Mohammed. Thank you for your delivery of useful and interesting keynote speech where you have focused on critical aspects regarding intelligent image enhancement and real-world applications. At this stage, I would kindly like to invite Professor Oswald Garvasi on the stage to present plaquette for Professor Khan Mohammed for his keynote speech. Take photo. You can take photo. Dear participants, this brings us to end of keynote speech section of ICCSA 2025 Day 3. Let me kindly inform you about the conference publication that 3 Springer books consisting the accepted papers have been published. They are online now. The remaining ones are the published, and it will be possible to download whole complete book within 1 month for only one time, right? After 1 month, it will not possible to download it. Before conclude, let me kindly remind you that we have our gala dinner at Point Hotel this evening to start at 8 p.m. Now I think we may please proceed to the lunch venue. Thank you very much for your kind attention and participation today.